Hello, today we are going to talk about what exactly is a naive Bayes model. So in our previous videos, we talked about how we can derive the formula for Bayes' theorem, uh, which basically is we derived from the formula of conditional probability, and you can see that formula here. But today we are going one step further and saying and explaining what is naive Bayes model. And I tried to explain it in the simplest way possible, just by cubes. Let's say we have a cube which has we have a square, sorry, not cube, square, which has a side of 9 meters. And some of those cells are colored in yellow, some of them are colored in yellow, purple, and green. Some of them are just colored with only red. It's a very good model to have a good understanding of Bayes model, Bayes theorem. So we start with the question, what is the probability that, oh, sorry, it's actually not part of the formula, because this is a different statement, different question that I posed there, but below I am explaining something else. But no worries, I will go through what I was trying to find and I will explain everything. Yeah, I'm just explaining it. So we are trying to find the probability of observing a yellow square, given that that square is green and red at the same time. We go back to our formula and we apply that formula to this problem. Then this formula turns into probability of observing yellow multiplied by the probability observing green and red, given that it's already yellow, divided by the probability of observing a square, which is 1 centimeter to 1 centimeter, the probability divided by the probability of observing green and red. Probability of observing a square that is both red and green. But what we do here, we have a very big assumption. And this assumption helps us to simplify the formula, and it makes it mathematically very simple and calculable. Of course, it does not reflect the true nature of probabilities all the time, but it gives us a very good advantage of simplified math. And most of the time it can gives us a good estimate with a very simple math. What we assume here is that the probability of observing green and red, given that yellow. Okay, we can calculate the probability of observing yellow by looking at how many cells we have in total, which is 81. And how many yellow cells do we have in total? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12. I just calculated this so you have an idea of how we can calculate the others as well. We can also do the same thing, probability of green and red, given that it's yellow. So what we do, we look at the yellow squares, and then we'll look how many yellow squares do we have in total. It's 12, right? And how many squares we have, which is yellow, green, and red at the same time. As you can see here, this part here is yellow, green, and red at the same time. So only two, this one and this one. And then look at this probability. What is the probability of observing green and red? What is it? We look at all of the cells, all number of cells, which is 81. And how many cells do we have which are both green and red? Let's look. It will be probably this part, right? 1, 2, 3, 4. So it will be 4. So I just explained this to show that that's how it's calculated. But in real life, calculating this is not always possible. And we have an assumption here that says the probability of observing green and red are independent. And if they're independent, then this probability can be expressed in a different way that I show below here. Probability of green and red, given that yellow, is probability of observing green given that yellow multiplied by the probability of observing red given yellow. If we assume the independence, then this formula turns into this, which is very which makes things way easier. So this is basically what a naive Bayes theorem is. I hope you understood a bit better with my simplified explanation. See you in the next videos.